Electric vehicles have come a long way, but their most critical component still sucks. Their batteries. Right now, EV batteries are heavy, flammable, slow to charge, and they don't last forever. However, things are about to change. There's a new technology called solid-state batteries, and they promise to make EVs lighter, safer, and able to charge in minutes. So in this video, we're going to tell you how they work, why they're so great, and when you might be able to buy one. Anyway, let's start by exploring current battery technology to fully appreciate why solid-state batteries will be so much better. Today, most electric vehicles are powered by lithium-ion batteries, which are batteries with a liquid electrolyte. For background, NASA researched this rechargeable battery technology as far back as the 1960s. However, it wasn't until the 1990s that Sony commercialized it for portable electronic devices. A few years later in 1998, lithium-ion batteries made their way into vehicles with the launching of the limited production Nissan Ultra EV. Today, lithium-ion EVs are everywhere, and I'll admit they get the job done, but they're far from perfect. There are many reasons that lithium-ion batteries are not well suited for automotive use. To start, lithium-ion battery packs can add lots of weight. Just look at the 9,000-pound Hummer EV. These batteries also degrade with age and eventually need to be replaced, which is a costly repair that can limit the lifespan of the car. Additionally, they're sensitive to temperature, they charge slowly, and they also need protection from overcharging or deep discharging. And to make things worse, some failure scenarios can lead to fires or explosions because there are highly flammable materials inside them. In fact, when I was in college, there was an electric skateboard with a lithium-ion battery that blew up in one of our auditoriums. Thankfully, nobody was hurt, but less thankfully, it didn't happen in my building, so I still had to go to class that day. Now, the dangers of lithium-ion batteries are often overstated because engineers have found ways to minimize these doom scenarios from happening. But that doesn't mean that solid-state batteries can't offer a more promising future. So let's learn how these rechargeable lithium-ion batteries work, and then we'll be able to fully understand why this new technology will make EVs so much better. Now, battery science can get complicated, so I'll keep it digestible. Don't worry if you can't understand immediately. I have a degree in electrical engineering and I still think it's hard. Batteries are energy storage devices that convert chemical energy to electrical energy, which powers everything in your electric vehicle. Rechargeable lithium-ion batteries can be broken down into 5 major components. These are the anode, cathode, the liquid electrolyte, separator, and the current collectors. The anode and the cathode are called electrodes, which are conductors that allow electrical current to flow. For this video, we'll define current as the flow of electrons, but technically it can be the flow of any charged particles. The anode is the negatively charged electrode where oxidation occurs. Oxidation means that electrons are being released, so you can think of the anode as the electron donor. In these batteries, the anode is typically made of graphite. The cathode is the positive electrode where reduction occurs. Reduction is the opposite process of oxidation, meaning the cathode gains electrons. Therefore, you can think of the cathode as the electron receiver. The cathode is also typically made of a lithium-containing metal and is where the lithium ions originate. Next, there's the electrolyte. The electrolyte is typically a liquid lithium salt and is responsible for carrying the positively charged lithium ions between the anode and the cathode. Think of the electrolyte as the lithium-ion pathway. However, you don't want electrons flowing through the electrolyte because then you couldn't access the electrical power. This is why batteries have a separator and current collectors. The separator blocks electrons from crossing directly through the battery and forces them to travel through the external circuit. This is how we extract usable electrical power. During discharging, positively charged lithium ions flow from the anode, which is at a higher electrochemical potential, to the cathode, which is lower. This potential difference is what drives the ion movement. Think of it like a ball sitting on top of a hill. The ball naturally wants to roll down to the bottom. It's moving from a higher energy state to a lower energy state. In a lithium-ion battery, the anode is like the top of the hill and the cathode is like the bottom. During discharge, lithium ions roll from the anode to the cathode, just like the ball rolling down the hill. This natural movement is what generates usable energy, and the electrons, which can't pass through the battery directly, take an external path to follow the lithium ions. And that's the electric current powering your car. Anyway, at this point, the positively charged electron-craving lithium ions are now on the other side of the battery. And since positive and negative charges attract, the negatively charged electrons want to join them. Basically, everything in chemistry wants to be balanced, and when the lithium ions move, the electrons want to follow. So when the lithium ions are flowing through the electrolyte, the electrons flow through the current collector to meet them on the other side. Remember, they must go through this external circuit because the separator blocks them from going straight through the battery. The electrons flowing through the current collector are what provides the electrical current, which powers the EV's various systems. During discharging, the same thing happens but in reverse. Electricity drives the lithium ions across the electrolyte from the cathode to the anode, and the electrons follow through the external circuit. Think of it like pushing the ball back up the hill. Now, solid-state batteries operate on the same fundamental principle. Lithium ions shuttle between the anode and the cathode to store electrical energy. In fact, they even share the same 5 components. But the materials, and especially the electrolyte, are different. Instead of using a flammable liquid, solid-state batteries use a solid electrolyte often made from ceramic, glass, or sulfide-based materials. Otherwise, their construction is similar, but this one key change is what leads to the major benefits of solid-state batteries, which we'll break down next. Solid-state batteries offer a promising future for electric vehicles because they outperform lithium ions in several key areas. To start, the solid electrolyte allows for a more compact cell structure, and some designs also integrate the separator into the electrolyte itself. This means that solid-state batteries can have over twice the energy density of traditional lithium ions. Secondly, solid-state batteries are proposed to be safer. Replacing the flammable liquid electrolyte with a less reactive solid electrolyte results in a design that has a greater chemical stability and is far less prone to fires or explosions. Another promising benefit is that solid-state batteries have demonstrated greater resilience to extreme temperatures. They also have the potential for faster charging capabilities and significantly longer lifespans compared to lithium-ion batteries. Combined, these developments have huge ramifications for the EV industry and could make electric cars more efficient, convenient, and safer than ever before. So if they're so great, why aren't they in production already? Well, that's a great question. Manufacturers are optimistic, but there are still a few hurdles the industry needs to overcome before we see them in our vehicles. The main issue surrounding solid-state batteries deals with their high expenses, complicated manufacturing processes, and their material limitations. The technology is still relatively new, so it requires some specialized manufacturing that is costly and difficult to scale. In fact, one of lithium-ion's biggest advantages is its mature manufacturing infrastructure. The industry has spent decades refining the designs and manufacturing processes to make it widespread and, most importantly, cheap. Another issue lies in crack formation within the solid electrolyte. These materials are often very brittle and are prone to cracking under mechanical stress or pressure changes. Obviously, these cracks are not good for the battery and can degrade its performance. Lastly, lithium dendrite growth is another major concern. Dendrites are little tree-like structures that can pierce the electrolyte, which can lead to battery failure or even fires. Despite these challenges, many big-name corporations are doubling down on the technology, and many people believe it won't be very long until we see solid-state batteries reach the EV market. Companies like Toyota, Samsung, BYD, and Solid Power are aggressively investing in the technology, and they hope to commercialize it in the next couple years. There is no denying solid-state potential. The possible improvements in energy density, performance, and safety have convinced many to develop the technology, and if successful, these batteries could be a game-changer in the industry. And now it's a race to get them developed and into production. Now I want to hear from you. Do you think this technology will live up to its expectations, or do you think it'll flop? Let me know in the comments below. If you enjoyed, please consider liking the video and subscribe if you want to see more of this content. Lastly, if you wanted to help financially support me and this channel, you could leave a super like or sign up for a channel membership, which has some nice benefits. It can be as little as a couple of dollars, and I'll be putting this money towards a new project car, which will be very exciting. Anyway, thank you so much for watching, and I will see you all next time.